Hello, I'm Kim Solez. I'm a physician author from Edmonton, Canada. This is my writing partner, Nikki Olson. We're very pleased to be bringing you this Lifeboat Foundation video on the artificial intelligence physician. There actually is more AI than it seems in existing medical devices.
When we actually build something that works, people say, well, that's just part of medicine.
We no longer call it AI. We just say, well, that's the new respirometer, the new dialysis machine, the new defibrillator, the new cardiac pacing device.
So if you blow into a respirometer and an AI diagnoses your pulmonary disease, people just say, well, that's just a respirometer.
And so many of these existing devices contain AI software, but we just don't call it AI.
When we're talking about an AI physician today, we're talking about what you would call narrow AI. Projects in the realm of narrow AI are in many ways more limited than what artificial intelligence programmers call AGI, or artificial general intelligence. The range of intelligent operations the software would be capable of would be restricted to a narrow domain, or perhaps even a small portion of that domain. Success in computational diagnostics includes correctly performing a red blood cell count, or automatically diagnosing an electrocardiograph. When people hear the term artificial intelligence, they often think of prototypes for more completed forms of AI, such as 2001's HAL 9000 computer.
I can feel it. My mind is going.
AI at this level, however, is not something that AI programmers will succeed at producing for many years. Much optimism exists, however, in the realm of AI and diagnostics. Many projects are underway to expand the domains in which software can behave intelligently. One day, perhaps, it is thought that AI could replace a doctor completely.
Well, I better have a look at you. Open your mouth, say ah.
Pattern recognition software is one of the important features in the development of the AI physician project.
The oracle in the matrix is presumably a neural network.
Bingo.
Artificial neural networks, or what computer programmers sometimes call the connectionist computing method to AI development.
Because she's a program that is intuitive rather than mechanistic. Neural networks can do a lot of stuff. They can pour through huge databases.
Computers can be made to surmise patterns in large amounts of data, and then come to have knowledge about a particular thing based on those patterns. And they can do so without very much input from us. One of the more famous robots today using pattern recognition technology is DARPA's Big Dog project. The robot is going out into the world and having experiences in the world, and then adjusting its internal programming to account for those experiences, thereby getting better at them each time. The robot is essentially learning, and perhaps it's not learning in the same way that the human brain learns how to do things, but the outcome in many of these circumstances is remarkably similar.
In pathology, for decades we've been using a microscope, and it has objectives with fixed magnification and focus, and it's basically a rather private and local enterprise and interaction between the slide and the microscope and the person using the microscope. Well, now all that's changing with the virtual microscope and the virtual slide. So this now shows one of the popular forms of the virtual microscope and virtual slide. Here we have a scanned image of a kidney transplant biopsy, and you can see that we're observing it at 3 different powers. There's high mag, medium, and low here. We have these areas with annotations where we have something that we want to specifically show, and that's fairly easy to do. And then we can go back to any magnification. We can zoom up and down, infinitely modifiable in terms of the exact magnification used. It's very easy to put on annotations, and you never get confused the forest and trees problem because of the fact that you're always seeing these 3 different magnifications at the same time. And this has largely replaced then the traditional real microscope. This image will never fade. You can share it with thousands or potentially millions of people on the web, and there's no chance of it getting lost. All the things that the real slide is vulnerable to, this virtual slide in the virtual microscope is not. So we really have come a long way from the time when the best we could do was to connect microscopes with tubes in order for a number of people to look at the same image. Now the prospects are really unlimited. So when you think about this virtual transplant pathology business, what could software really do? You know, when you look at a report on a kidney transplant biopsy used for actual care of a patient, it has so many components. It's kind of like a story, a narrative, and with many different aspects, and it uses the entire expertise and knowledge and insights that pathologist has up until that point. Well, software would never be able to do that anytime soon. On the other hand, for clinical trials where you're filling out standardized forms with numerical data in a highly stylized, reproducible way, that is something that software could learn how to do. And you could then use that, the prototype of the forms used for clinical trials, for mentoring of young people trying to learn the skill of kidney transplant pathology worldwide, where they would read the stuff, the software would give an opinion, and then someone like me could arbitrate between the two, and in that way effectively teach people all over the world that I wouldn't have the opportunity to do if the software did not exist. So this gives you some idea of how the practical side of virtual pathology might actually work. So this has been Kim Solez and Nikki Olson bringing you our musings on the artificial intelligence physician.